this video we're going to introduce the idea of homotopy. So this is how I'd like to define it. Okay, so x and y are going to be topological spaces. Okay, and then we're going to recall if we look so top x, y, we're using this kind of categorical notation. This is just a set of continuous maps. Say f from x to y, and so we're going to say that that f and g are homotopic if they lie in the same path component. Of top xy, i.e. there is a continuous path u from unit interval to top xy with u0 equals f and u1 equals g. Okay, so this would be nice if we could use this definition here, because then we could use all the stuff that we proved previously about path components. Unfortunately, there's a problem with this definition, in that we're talking about continuous maps to top xy, but top xy at the moment is only a set. Okay, it's not a topological space. We haven't introduced a topology on top xy. In some particular cases, we've just you've seen topologies on top xy, in particular in the metric spaces. People talk a lot about CXR, the set of continuous maps from x to r, which in our current notation would be top xr. And there's a metric on top xr, and there's a bunch of stuff in functional analysis or metric space theory about that metric and the corresponding topology. But for more general topological spaces x and y, it's actually rather difficult to introduce an appropriate topology on top xy. It can be done, but it would require a kind of huge detour into other considerations. So we're not going to quite use this definition. So let's just write it here. So this is invalid, as we have no topology on top xy. So we're going to have to introduce a different definition, which is technically different, but you should think of it as kind of being a substitute for the fact that we'd like to be doing this, but we don't have the right topology in order to do so. Okay, so here's the actual definition that we're going to use. So let's let f and g from x to y be continuous maps between two topological spaces, of course. So then a homotopy from f to g is a continuous map typically called H, from 0, 1 cross x to y, with H of 0x is f of x, H of 1x is g of x, for all x and x. And we say f and g are homotopic if such an H exists. And we might write so at least temporarily we'll use this symbol with a kind of 3-barred equals to say f and g are homotopic. So the first issue we need to check is that this is actually an equivalence relation. So it's a equivalence relation on the set top xy of all possible continuous maps from x to y. So firstly, well, we need to show it's so we have saying it's the equivalence relation. We have to show it's reflexive, symmetric, and transitive. In other words, that well, f any function is homotopic to itself. That if f is homotopic to g, then if g is homotopic to f, and also that if e is homotopic to f, which is homotopic to g, then e is homotopic to g. So for the first of these, if we just do ht comma x equals x as f of x is a so we can just define a function like this, ignoring the t. So this gives us a homotopy called the constant homotopy from f to itself. Okay, so the relation's reflexive. And then if h is a homotopy from f to g, then we can just define h bar of tx is h of 1 minus t comma x. That gives a homotopy from g to f. Okay, so that proves that this relation is symmetric as well as being reflexive. And then we just need a little bit more work to check that it's also transitive. Okay, so for transitivity, let's suppose h is a homotopy from e to f, and k is a homotopy from f to g. So then we're going to define k star h. It's going to be a map from 0, 1 cross x to y. So k star h of t comma x. So if you have to divide it in two parts. So if t is between 0 and a half, then we do h of 2t x, and if then in the second half of the interval we do k of 2t minus 1. And so we do need to check that these two clauses are consistent. And then so the first clause is going to give us h of 1x, but remember h was a homotopy from e to f, so that's just the same thing as f of x. And the second clause will give us k0 comma x, but k was a homotopy from f to g, so k0x is going to be equal to f of x. So so both of these clauses give us the same answer when t is a half, so that's a self-consistent definition. Okay, and this is continuous by closed patching. Okay, so in these two subsets, 0 a half cross x and a half 1 cross x, those are both closed. And it's pretty clear that this map is continuous on each of these two closed subsets, so that we have this closed patching proposition, which said in that kind of situation we can conclude that the whole map itself is continuous. And also, if we look at k star h of 0x Okay, well then we're in this first clause, so we get h of 0x, which is e of x, and k star h 1x. Well, then we're in the second clause, so we get k and then twice 1 minus 1, which is 1, comma x, and then k was a homotopy from f to g, so this is equal to g of x, i.e. K star h is a homotopy from e to g. Okay, so that completes the proof that this relation of being homotopic, that's an equivalence relation. So as usual, we're going to just write square bracket f is the equivalence class of f, and that's typically referred to as the homotopy class. And we also will sometimes write square bracket xy is the quotient set, top xy, taking the quotient by this equivalence relation. In other words, that's just a set of homotopy classes. Okay, so now we'll give an example where it's fairly easy to kind of at least see what's going on, even though it'll take us a little while before we can kind of prove that it really works as you think it does. But so this example, we're going to take x is the circle and y is the non-zero complex numbers, or the plane with the origin removed, if you like. And as before, so xy is S1 C less naught is the set of homotopy classes Okay, so what does such a thing look like? I mean, so so like here's the complex plane. We've removed 0, and so we've got a path. So path is, it's got a particular direction to it. It's a direction of kind of increasing theta as you go around the circle, say. So for a u from S1 to C less 0, put n of u is the winding number. So it's the number of times u winds around the origin with anti-clockwise counting plus, clockwise counting negative. Okay, so this one, so this u here, this has, this goes around the origin twice anti-clockwise, so n of u is 2. Okay, so it'll take a little work to kind of make this definition really properly precise, but at least for reasonably simple pictures, it's pretty easy to see what we mean. And so, it's clear, right? Well, suppose we do a homotopy to this u. We sort of continuously move the loop around. Well, we can change all sorts of details about it. Maybe we can draw another picture. And so there's a different loop v which also goes around twice. And you should be able to see, we could just pull, if we imagine these loops being made of string or something, or rubber bands, then you could pull the U around and move it a bit, and so as it overlaps with the V. So your U and your V are actually homotopic here. And what one can check, U and V are homotopic if and only if and they have the same winding number. And in fact, we can define pk, say from S1 to C less 0. So if we think of the if we think of S1 as being the complex numbers of absolute value 1, then we can just use this formula. Pkz is z to the k, the kth power map. Okay, so that so you see that kind of winds around k times. So the winding number of pk is k. Okay. So using these things, if we believe them, say will take us a little bit of work to check that this is really true, but we'll do that later. But it should be at least plausible that if we believe that, then this is telling us that this map here, the winding number map from this set of homotopy classes to Z, is a bijection. So that's a kind of interesting example where we've got a non-trivial answer for a set of homotopy classes between two spaces. So one other kind of construction that we'll use in various places is linear homotopies. So let's just discuss that. So now let's suppose that Y is a subspace of the Euclidean space Rn. Okay. Then if we've got two continuous maps, say f and g from x to y, then we can define a map h from 0, 1 cross x to Rn by h of t x is 1 minus t f of x plus t g of x. Okay, so this is kind of on the straight line from fx to gx. So typically, of course, the image of h is not contained in y. Okay, there's no reason in particular why this image of this map h should be contained in y, and so this h is typically useless. But in some cases, we can prove that in some cases we can prove that the image is contained in y, and then of course we have to write a careful argument for that in any particular case, and then h gives a homotopy, which we'll call a linear homotopy, from x to y, from f to g. But in particular, one case in which this always works, if y is convex, so remember what that means. As space is convex, if let's draw a picture of a typical convex set. This is a convex set. You choose any 2 points in it. Then a straight line between those 2 points is wholly contained within the set. Okay, so that's so if y is convex, then there's a linear homotopy between any two maps. And so in that case, you look at the set of all homotopy classes. Well, all possible maps are, also, I guess I should have said here. I mean, a convex set by definition is, it's part of the definition of a convex set. It's got to be non-empty. Okay, so there's at least one point in Y. So we have got a constant map, just sending everything in X to that point. So there's at least one map from X to Y. And in fact, any two maps are equivalent. So this is just this is a one-element set. So that's another case in which we can understand exactly what square bracket xy looks like. Although, of course, this answer is not terribly interesting. It's just telling us that the space Y is kind of, in terms of homotopy theory, it's just not very interesting. It's contractible in the sense that we'll discuss in a minute.